Hey guys, welcome to video 68. Today we're going to talk about how to estimate tube parameters using the plate curves and our Q point location. In particular, we're going to be talking about triodes and the small signal parameters transconductance, dynamic plate resistance, and mu, the amplification factor. So over here on the left-hand side of the page, we've got the typical cathode feedback biased triode, and beside it we've got the small signal model using the voltage controlled current source representation. Now if we decided to use, say, a 12AX7 because that's a very popular tube, if we check its data sheet, we'll find that we're given average values for mu, transconductance, and little rp for two different plate to cathode voltages, 100 volts and 250 volts. Notice that mu doesn't change over this range of voltages, but transconductance and little rp do. Now, in all honesty, this is enough information for us to do good design of just about any guitar amplifier, but if there was some reason you wanted to know your tube parameters a little more accurately based on Q point location, we could also do that. Now, why would you want to do that? I don't know. It's a good academic exercise that's just gives you better insight into the way tubes work. That's one reason. And who knows, maybe sometime in the future you would decide to design a vacuum tube GPU to compete with NVIDIA, or maybe a vacuum tube based quantum computer or something. But in any case, we can derive values for these parameters using the plate curves for the tubes, and that's what we'll do next. But first we need to take a look at the parameter definitions. Now, over here on the right side of the page at the top, we've got the parameter definitions, and notice they're all based on derivatives. For example, mu is the derivative of VPK with respect to VGK, with plate current held constant. Now, these are great if you're deriving things from first principles using vacuum tube physics, or maybe even designing vacuum tubes themselves. But we're just looking at the tube as a circuit element, and we're going to use these approximate relationships in conjunction with the plate curves to estimate all these parameters at a given Q point. So let's go on over to the next page, and we'll start with the curves for a 12AX7, and we're going to determine mu based on two different Q points here. Now, I've located the Q points on just an arbitrary load line. It really doesn't have any significance. And let's start with this green Q point here. It's located with a VPK of about 100 volts and an IPQ of about 1.2 milliamps or so. Now, what we're going to do is determine the change in VPK for a given change in grid to cathode voltage. So the most sensible way to do this is to use the grid curves located on either side of our Q point. So moving to the left, we've got the VGK equals 0 curve, and moving to the right, we've got the VGK equals -1 volt curve. All right, so we've got a delta VGK of 1 volt, and that corresponds to a delta VPK moving from 50 volts to 150 of 100 volts. So our mu for this Q point is approximately equal to delta VPK 100 volts divided by delta VGK 1 volt, which is a mu of 100, and that's the typical value given for the 12AX7, so we shouldn't be surprised. Now, if we move over here to this red Q point located at a much higher VPK and lower plate current, we find that for a 1 volt change in VGK, that is a grid voltage change from -2 to -3, that would correspond to a change in VPK of 175 volts to 270 volts, which is a 95 volt change, and our resulting mu value would be 95 volts divided by 1 volt, which is 95. So mu is a little bit lower over here, and it's still pretty close to 100, so that's why in the data sheet it's listed pretty much constantly as having a value of 100. But if we did want to know it more precisely, we can see that does change a little bit, and over here it's closer to 95. Now let's go on over to the next page and determine transconductance for these two different Q points. Let's start by looking at our GM equation, which is delta IP over delta VGK. So what we're going to do is find a change in grid to cathode voltage and find the resulting change in plate current. So beginning with the green Q point, we'll use the curves on either side of our Q point curve. So that's VGK is 0 volts and VGK is negative 1 volts, so we've got a delta VGK of 1 volt. And that corresponds to a plate current change from 2.1 milliamps to 0.5 milliamps, which is a delta IP of 1.6 milliamps. So our GM for this Q point is 1.6 milliamps divided by 1 volt, or 1.6 millimos. Moving over to the red Q point, if we use the grid to cathode voltage curves on either side of our Q point curve, we find that again we've got a delta VGK of 1 volt. We're going from negative 2 to negative 3 volts, and that corresponds to a plate current change from 0.56 milliamps down to 0 milliamps. So we've got a 0.56 milliamp delta IP. And our corresponding transconductance then is 0.56 milliamps delta IP divided by 1 volt delta VGK, which is 0.56 millimos. Now let's compare the GM values we just figured out with the ones given in the data sheet at the same VPK values, or close VPK values. For our green Q point, we have a VPK Q of about 100 volts. And according to the data sheet, at 100 volts, we should have a GM of 1.25 millimos. We came up with 1.6. So they're not too far off. But let's go over here and look at our red Q point, which is around 220 volts or so. And that should be close to the 250 volt value given on the data sheet, which is 1.6 millimos, but we got 0.56. Now, that's a pretty big difference, even though the voltages from plate to cathode are about the same. But what we're seeing here is that the plate current has a pretty large effect on transconductance as well, and at low plate currents we tend to have a low transconductance. That is, if we look at how steep these curves are, at low currents the slope is pretty shallow. So at low currents we have a low transconductance, and that's reflected over here. So really this is more accurate for our Q point location than the value that's given on the data sheet. And that's something you may want to keep in mind when you're actually designing amplifiers, and your Q point is located at a low current versus a high current. You may want to go ahead and determine the transconductance based on your Q point location rather than relying on these typical parameters. And something I probably should mention just for the sake of completeness and technical precision here is that since we're calculating these values based on specific VPK values here, we should put that into the equations instead of this generic constant label. So if I were turning this in for a grade, for example, I would, for my green Q point, enter VPK equals 100 volts, and for the red Q point, VPK is 220 volts. So I would make these substitutions, but in this case it really doesn't matter. So let's go on over to the next page and we'll calculate our dynamic plate resistance for these two Q points. This time the equation we're using is little rp equals delta VPK over delta IP, and we're holding VGK constant. That means we're moving along the grid bias curve that our Q point is located on. So in the green Q point case, we're going to just pick an arbitrarily convenient interval, say on the VPK axis, and find the resulting change in our plate current. So in this case, if we move around our Q point from 75 volts to 125 volts for VPK. That gives us a change in plate current from 0.8 milliamps to 1.65 milliamps. And our resulting dynamic plate resistance is delta VPK 50 volts divided by delta IP 0.85 milliamps, or 59,000 ohms. Coming over to our red Q point, we're going to be moving along the VGK equals negative 2.5 volt curve and choosing a convenient interval on the VPK axis that surrounds our Q point. If we go from 200 volts to 250 volts, that gives us a corresponding change in plate current from 0.1 milliamps to 0.5 milliamps. So our delta VPK is 50 volts, delta IP is 0.4 milliamps, and the resulting dynamic plate resistance is 50 volts over 0.4 mils, and that's 125 k ohms. Now, if we look at these RP values and compare them to the typical values given on the data sheet, we don't have a super great correlation here, at least in terms of VPK. But if I pull up the data sheet for a second here and we look at the average values for these parameters, notice they are given at different current values as well, although the low voltage is corresponding to a lower current here, and the higher voltage corresponds to a higher current. So, it's kind of hard to pick which of these things is the most meaningful. And because of that, I think, a lot of times just look at your curves and do these calculations. They're not that bad, and you can get pretty good estimates. But in any case, the trend we notice here is that at lower plate currents, we tend to get a higher little RP value. Now, there is another way that we can get pretty good estimates of our Q point small signal parameters other than using the plate curves like we've been doing, and that is to use the characteristic curves that are given on most data sheets. And here's an example for the 12AX7. Now, on the left-hand side are the plate curves with our hypothetical load line and Q points. Then over here on the right are the characteristic curves from the data sheet, which are a graph of mu, transconductance, and dynamic plate resistance as a function of plate current for some particular fixed plate to cathode voltage, in this case 100 volts. Now, I've marked off my Q point currents here on the horizontal axis. Our red Q point has an IPQ of 0.25 milliamps. Our green Q point has an IPQ value of 1.2 mils. And let's start with the green one here. All right, so if we go up from 1.2 milliamps on the x-axis straight up, we find where we intersect all of these curves, and those will be our small signal parameters. So the intersection for little rp is approximately 58 k ohms. We'd get that from this scale over here, and that's in good agreement with the value we derive from the plate curves. If we go up a little bit further, we find we intersect the transconductance curve at about 1.7 millimos, and we'd use this scale over here. It's marked in micromos, but that's the same thing. And that's in good agreement with the value we derive from our plate curves of 1.6 millimos. And finally, if we keep coming up, we hit the mu curve, and that's got a value of about 100, which we also calculated based on our Q point and the plate curves. Now, going to the red Q point, we've got an IPQ of 0.25 milliamps, and if we come up from there, we intersect the transconductance curve at about 0.92 millimos. It's a little bit higher than the value that we computed from the plate curves, but I would expect that to possibly be off a little bit because these curves are for a plate to cathode voltage of 100 volts. We've got a plate to cathode voltage here of 220 volts. So I would suspect that the value we estimated from the plate curves is a little bit more accurate in this case. But in any case, it's not too far off. So if we keep going up, We have a mu value that's a little bit less than 100, say 95, and that agrees well with our value that we estimated from the plate curves. And finally, our RP value works out to be about 108 k ohms on this graph. Again, we'd read it from this scale. And it's a little bit less than what we calculated based on the plate curves, but again, we have to consider that these curves, these characteristic curves, are for a plate cathode voltage of 100 volts, and over here we're operating at 220 volts. So that's an alternative for calculating or estimating your small signal parameters at a given plate current. And finally, I'm going to leave you guys with a homework problem. Here we've got a hypothetical load line for a 12AU7, and the Q point is located at 4 milliamps and 175 volts. So you'll have to check the 12AU7 datasheet if you want to use the characteristic curves, or again, you can derive them directly off of the plate curves here. And by the way, here are the characteristic curves for the 12AU7. This is pretty interesting. Let me pull it down. And there we go. So this is the mess that you have to work with to figure out these values based on the characteristic curves for the 12AU7. Or again, you could just use the techniques I showed you earlier with the plate curves and go from there. But that's it for today's video, and I'll see you guys next time around.